Okay, so this is a small video to help clarify what we'll be doing with stoichiometry and limiting reagents. Stoichiometry is just using a series of conversion factors to convert from one unit to another. For example, last year we converted from moles to mass using the mole formula. We converted from moles to molarity using the molarity formula. And I'm not saying that we're not going to use these individual formulas this year, but a lot of what we're going to be doing is converting from one unit to another. Let's say I want to figure out, if I've got a certain amount of grams that I'm starting with of a substance, how much product can be produced. I would use dimensional analysis and stoichiometric relationships in order to do that. Or perhaps I wanted to figure out how much excess reagent there would be. Say I'm mixing two things together, I use one reagent completely up and then I have excess of another. I might want to find out how much of that reagent was unused. What's going to be very important is we're going to be converting from grams to moles or moles to grams, and we need to know that 1 mole equals the gram formula net mass. We also need to know that 1 mole equals Avogadro's number, 6.02 times 10 to the 23rd atoms or molecules. A lot of times we'll be converting between moles, moles of substance A to moles of substance B in a reaction, and we're going to use the coefficients in that balanced equation to help us do that. Additionally, we might be converting between moles and liters, or liters and moles. Remember that 1 mole equals 22.4 liters if it's a gas. Sometimes we'll be using the molarity formula to figure out how many moles of a substance I'm starting with if it's a solution, and then use dimensional analysis to finish the problem. So just to recall what dimensional analysis is, let's look at this problem where I want to convert 347 centimeters to yards. Now, in order to go from centimeters to yards, there's a couple of conversion factors that I need to know. I need to know that 2.54 centimeters equals an inch. I need to know that there are 12 inches in a foot, and I need to know that 3 feet equal a yard. And I can use these interchangeably. I might have 2.54 centimeters over 1 inch, or I could have 1 inch over 2.54 centimeters. It really depends on the units in the equation, what I'm starting with and where I need to be ending up. So if I'm starting with 347 centimeters, in order to get centimeters to cancel, I need to have a unit of centimeters in the denominator. So I can say 2.54 centimeters equals 1 inch. And my centimeters cancel. I can go now, I don't want inches, I want yards, so now I can say 12 inches equals 1 foot, and my inches cancel. And my last conversion factor is 3 feet equals 1 yard. My feet cancel. And I'm left with units of yards, which is what I wanted to have. Now it becomes a multiplication problem. 347 times 1 divided by 2.54 divided by 12 divided by 3. And this is going to give me 3.85 repeating, so we'll make that 3.86 yards. So that is an example of dimensional analysis. Let's see how we might use this in chemistry. I'm going to read you a problem. It says methane, which is CH4, reacts with oxygen, which is O2, to form carbon dioxide and water. I had to put a 2 in front of the water because I have 4 H's on the left, I need 4 H's on the right. That now gives me 2 O's here and 2 O's here for a total of 4 O's, so I put a 2 here to give me 4 O's. I'm starting with 72 grams of water, and they want to know, if I produce 72 grams of water, how much methane must I have started with? Well, there's 2 ways that you can do this problem. I'm not saying that you have to do it one way or another, but I'm going to show you the way that makes sense. Now this is an easy problem. Since I need my answer in grams, I can simply set up a proportion. I know that I have 2 moles of water. I know that water has a mass of 18. 16 for the oxygen and the 2 hydrogens makes 18. There's 2 of them. 2 times 18 is 36. So 36 grams over 72 grams equals, I have 1 mole of methane, this is 12, and 4 is 16 grams over X. I can cross multiply and divide and get my answer of 32 grams. In this case, it's a very simple problem. Maybe I might want to do that. I find out that dimensional analysis is really easy to use. By starting with 72 grams, I'm going to do just like I did in the centimeters to yards problem. I want my grams to cancel. Well, what do I know? I know that 1 mole equals the gram formula mass. So this is 72 grams of H2O. I know that 1 mole of H2O has a mass of 18 grams. My grams cancel. Okay? I'm not where I want to be yet. Remember, I'm trying to get to grams of CH4. Now I'm going to use the coefficients. I'm going to do that intermediate step, mole, mole, right here. I just changed mass to moles in this problem. Mass to moles. Now I'm going to use a mole-mole relationship. In my problem, in my equation, I have 2 moles of H2O, and I have 1 mole of CH4. My moles of H2O cancel. I'm not where I want to be yet. I want to be at grams of CH4. What I know is 1 mole of CH4 has a mass of 16 grams. So now my moles of CH4 cancel. I'm left with grams of CH4, which is what I'm trying to find. So what this winds up being is 72 times 16. 72 times 16 divided by 18 times 2. When you do the math on this, you're going to come out with 32 grams of CH4, which is exactly what I got when I set up a proportion. Let's look at a different problem. We're going to look at hydrogen, which is H2, reacts with oxygen, which is O2. Because they're part of Brinkelhoff, we have to write them as diatomic compounds, form water. Now we need to balance the equation. We need to put a 2 here, so we have 2, and then that's 4 H's, so we need a 2 here. If 16 grams of hydrogen, so we have 16 grams of H2, is mixed with 16 grams of O2, how much water can form? So we don't know how much water can form. In this equation, we have to find the grams of water that's produced. The problem being is we have the mass of 2 reactants, and they are not at a 1-to-1 mole ratio. They are at a 2-to-1 mole ratio. So that means for every 2 moles of hydrogen, you need 1 mole of oxygen. So we have to figure out what is going to be the limiting reagent in this problem. The limiting reagent is exactly that. It is the reagent that limits the reaction. Because of its quantity, it determines how much product will be produced. So the easiest way to do this is to calculate the number of moles of each of the reactants and then divide by the coefficient to see which one is present in the smallest quantity. So for example, for O2, if we take the 16 grams that we're starting with and we divided it by the GFM, because this is just simply moles equals given mass divided by GFM. So 16 divided by O2, O2 is 32 grams. That gives me 0.5 moles of O2. If I do that with hydrogen, I've got 16 grams of hydrogen divided by the mass of hydrogen, H2, is 2 grams. So 16 divided by 2 is 8 moles. But we have a coefficient of 2 in our equation, so really, when this combines, I would need 0.5 moles of O2 and 4 moles of H2. So this is present in the lesser quantity, so this is denoted as my limiting reagent. So, in order to determine what amount of water will be produced, we're going to start with our limiting reagent. And I'm going to see if I can fit it in over on the side here so you can see everything. So I'm going to do it right here. I've got 0.5 moles of O2, and I need to figure out grams of H2. So I have to do a molar relationship. I've got 1 mole of O2 from my equation going to 2 moles of H2O. My moles of O2 cancel, and I need grams, and we know that 1 mole of anything equals the gram formula mass. So 1 mole of water is equal to 18 grams. And now my moles of water cancel. So I've got 0.5 times 2 times 18, which gives me 18 grams of water as my final answer. Let's look at a different type of problem that involves a precipitate. How many moles of barium sulfide will form when 60 mils of a 1 molar barium nitrate solution are mixed with 25 mils of 0.8 potassium sulfide solution? So let me write down, we're mixing barium nitrate, which is BaNO3, and potassium sulfide, which is K2S, and we're forming barium sulfide, BaS, this is a double replacement reaction, and potassium nitrate. Let's balance our equation. We've got 2 Ks, so I got to put a 2 here. I have 2 NO3s, good, I'm balanced. They're telling me that I'm starting with 60 milliliters of 1 molar BaNO3. And I'm also starting with 25 mils of 0.8 molar K2S. So the first thing that I want to do here is figure out how many moles. I need to figure out what is the limiting reagent. Is my K2S the limiting reagent, or is my barium nitrate? So let's get this into moles. Now notice I've got molarity and milliliters. So using molarity, moles over liters, right? I can figure this out. If I have 1 molar equals X, milliliters to liters, I divide by 1,000 is 0.06 liters. So this is going to give me X equal to 0.06 moles of BaNO3, and I also have 0.8 molar equals X, and this is 25 mils, 0.025 liters. So I'm going to have 0.8 times 0.025, which gives me 0.02 moles of K2S. So this is my limiting reagent. That's really important. Now they want to know how much barium sulfide will form. So they want to know, let me see if they're asking for moles or grams. How many moles of barium sulfide? So we're trying to find moles of barium sulfide. So we're going to use dimensional analysis, starting with my limiting reagent. 0.02 moles of K2S. I'm going to use a molar relationship from the balanced equation. We have 1 mole of K2S in our balanced equation, and we have 1 mole of BAS. So technically, we could have just looked at the equation and saw that the K2S and the BAS was a 1-to-1 relationship. So whatever moles of K2S I have, then my moles of BAS must be the same. So this is simply going to be 0.02 moles of BAS. Similarly, I could have asked how much KNO3 was produced, and because the K2S and the KNO3 is a 1-to-2 relationship, I could very easily deduce that 0.04 moles of KNO3 would be produced. All right, let's look at yet another type of problem. In this equation, there's a little bit of a spin because they're going to ask for the excess reagent. If I have sulfur atoms and oxygen molecules, so I've got sulfur combining with oxygen, which is going to be O2, to form sulfur trioxide. Sulfur trioxide, so that's going to be SO3. They want to know some things. So they're telling us that we're going to have 7 moles of this sulfur, and we're going to have 10 moles of oxygen. And they want to know if the maximum amount of sulfur trioxide is produced, then how much reactant remains unused? How many moles? So they want to know how many moles of excess reagent is left. Unused. Excess means it was unused. So that means we're talking about S or O2. In order to solve this equation, the first thing we need to do is balance it. So we're going to put a 2 here, because 2 times 3 is 6, and a 3 here, because we had an uneven number here, so we have to go with the least common multiple. And then we need a 2 here. So once again, in order to determine what the excess is, we have to determine what our limiting reagent is. So if I take sulfur and I take 7 moles and I divide it by 2, I'm going to get 3.5. If I take oxygen and I take 10 moles and I divide it by 3, I'm going to get 3.3. So this is definitely my limiting reagent, my oxygen. So the easiest way to solve this problem, once I know what my limiting reagent is to take how much I'm starting with. So I've got 10 moles of O2, and figure out how many moles of S would I use. Well, in my balanced equation, I have 3 moles of O2, because we want those to cancel, going to 2 moles of sulfur. So 10 times 2 is 20, divided by 3 means that I'm going to use 6.67 moles of sulfur. So if I use my entire 10 moles of oxygen, I need to combine it with 6.67 moles of sulfur. Well, they're asking me how much excess reagent is left. Well, 7 minus 6.67 is going to give me about 0.33 moles of sulfur in excess. Okay. Now, there's a slightly different type of problem where we use dimensional analysis that's interesting. It's not so much determining how much of something else you have, but how much of something in something you have. For example, in this problem, if I have sucrose, C12H22O11, and I tell you that it has a gram formula mass of 342 grams per mole. So that's the mass of the sucrose. And I want to know how many atoms of carbon. So X atoms of carbon in 684 grams of sucrose. So let's see how we would solve this. We're going to start with our 684 grams of C12H22O11. And what I can say is this has a mass of 342 grams of C12H22O11. And in that, how many grams of carbon are there? Well, there's 12 carbons, and each carbon has a mass of 12. 12 times 12 is 144. So there are 144 grams of carbon in C12H22O11. But I don't want grams. I want atoms. Well, what else do I know? I know that 1 mole equals the GFM, and the GFM of carbon is 12 grams. And I also know that 1 mole equals 6.02 times 10 to the 23rd atoms. So in this problem, my grams of sucrose cancel with my grams of sucrose, my grams of carbon cancel with my grams of carbon, and this was moles of carbon, and they cancel, and I'm left with atoms. So 684 times 144 times Avogadro's number divided by 342 divided by 12. My final answer on all this math is going to be, and that would be atoms of carbon. Okay, I'm going to do one last problem, and that will be it for today. In this problem, they want to know how many grams of chromium are in 58.5 grams of potassium chromate. So I'm starting with 58.5 grams of potassium chromate, and I know the gram formula mass of potassium chromate. They give that to me, so K2Cr2O7 is equal to 294 grams per mole. So what I know is that 294 grams of K2Cr2O7 contain 2 chromiums. Well, each chromium has a mass of 52, so Cr, we've got 2 times 52, which is equal to 104 grams. So within this compound, I have 104 grams of chromium. So my grams of potassium chromate cancel. 58.5 times 104 divided by 294 gives me 20.69 grams of chromium, or approximately 20.7 grams of chromium. Okay, that's it for today. We will continue with some more problems in another video. Again, if you have any questions as you're going through this, please don't hesitate to ask. I apologize for any background noises in today's video. I did it while I was at work. Have a great day.